Hi, everyone. So we've been talking about finding antiderivatives and evaluating integrals using the FTC. But the integrals that we've been doing so far have been relatively simple. I've been kind of sticking to problems where we were able to just use a power rule to find the derivative or the antiderivative. But what happens if we have something a little bit more complicated? So what if I gave you the antiderivative or the integral of x squared plus 5 raised to the third power times 2x dx? We could multiply all this out if we wanted to, but that would be really time consuming and definitely cumbersome. So there's another method that we can use called U-Substitution. And I'm just going to give you guys a little bit of an intro to U-Substitution today, and then we'll kind of be working more with it when I see you next week. So generally, when we are given a more complicated integral or something with maybe like a composition or maybe something with like a square root, this is generally where we would want to use the U-Substitution. And generally, like what U-Substitution is we're going to be picking part of our integral to actually replace with a different variable, and that would be the variable u. My general rule of thumb is when I'm looking for something to replace, usually I'm looking on the inside of a set of parentheses. And I'll kind of talk you through kind of what that means when we look at some examples. So usually I'm looking inside of a set of parentheses or maybe like inside of a square root. And what I'm going to do is I'm going to use that quantity that's on the inside of the parentheses, and I'm going to call this quantity u. So my first step here is to identify something that I want to replace with u. So I'm going to say u is going to be x squared plus 5. And what I'm going to do when I replace or take out the quantity that I want to call u, I'm actually going to take the derivative of this quantity and I'm going to take it with respect to x. Meaning I'm just going to take the derivative of both sides of this equation. So I'm going to say, all right, what's the derivative of u? I'm going to call that du. And then I want to take the derivative of this side, and that's going to be derivative of x squared is going to be 2x. Derivative of 5 is just 0. And then I'm going to take this with respect to x, so I'm going to call this dx. So the derivative of du is du. Derivative of x squared plus 5 would be 2x dx. And what I'm going to do is I'm going to take this quantity that I just got and I'm going to solve for dx. So meaning I'm going to go ahead and I'm going to divide each side by 2x. So this gives me dx equal to du divided by 2x. And depending on what the function is, sometimes we might want to play around with this a little bit and kind of take out any constants that we have. But the reason that we do use substitution and the reason that we solve for dx is now that we have what u is equivalent to, and now that we have what dx is equivalent to, what we're going to go and do now is we're going to go back and simplify this integral by actually substituting in what dx is equal to and substituting in what u is equal to. And we'll see that something actually pretty nice happens. So now I'm going to go and actually substitute in u and dx into the integral. So I'm going to take my integral. This whole quantity we're going to call u, and we're going to raise it to the third power. I'm going to keep the 2x there because I didn't do anything with that 2x that was next to our quantity cubed. But I'm going to go ahead and I'm going to replace dx with what I know it's equal to. So I know it's equal to du divided by 2x. And the reason that U-substitution is nice and the reason that we do this process over here is if you notice over here, when we substitute in what we have for u and dx, these two quantities of 2x actually end up canceling out. And what we're left with is a much simpler integral than what we started with. What we're left with is just the integral of u to the third du. And that's something that we can take the antiderivative of. That's an easy function to use the power rule on. So up here, I'm going to just write cancel any terms you can. And then at this point, once you have something that's simplified and you have something that you can actually take the antiderivative of, then we're going to go ahead and take the antiderivative. I'm just taking the antiderivative here with respect to u because that's the variable that we're working with right now. So using my power rule, this is going to be, I think, 1/4 u to the 4th. And since this is an indefinite integral, I want to also include a plus c here. So the antiderivative of u to the 3rd du would be 1/4 u to the 4th plus c. But now I'm going to go ahead and I'm going to substitute in what I originally had called u. So I'm going to substitute my u is equal to x squared plus 5 back in, which means that my antiderivative of this x squared plus 5 cubed times 2x is actually going to be 1/4 of the quantity x squared plus 5 raised to the 4th plus c. So the reason that we like U-substitution is because it allows us to simplify something that's more complicated with rules that we already have been working with and practicing to get something that we are more comfortable working with rather than trying to expand this out and multiply everything out. And it's going to be useful with functions that maybe you can't multiply out anyway. So let's look at another example. So let's use the substitution method to find the antiderivative of sine of 3x plus 2 dx. So again, when I'm generally looking for something to substitute, I'm going to look on the inside of the set of parentheses. So the more you do these, the more you're going to be able to kind of see what you want to substitute. But for right now, I'm going to substitute u to be 3x plus 2. And then I'm going to go ahead and take the derivative of both sides of this. So du is going to be equal to derivative of 3x plus 2 is just going to be 3. And again, I want to take the derivative with respect to x. So I want to say that that's equal to 3 times dx, because remember, I want to solve for a dx here. So then I'll go ahead and solve for dx. So divide each side by 3. So that's going to give me dx is equal to du over 3. And like I was saying up here, sometimes you might want to kind of fool around with this dx a little bit, depending on what the function is. This one ended up working out pretty nicely because we knew that we had a 2x over here that we would eventually cancel out. If you don't have anything that you can kind of identify right off the bat to be canceled out, you can also say that this dx could also be equivalent to writing it as 1/3 du, which we'll kind of see this format is going to be a little bit more helpful in this case. So you can leave it as du over 3, but I'm going to show you why we would want to write that as 1/3 du in this case. So now that I know what dx is equal to, I know what u is equal to, I'm going to go ahead and substitute those into the integral. So I'm going to say this is sine of u, again replacing the 3x plus 2 with the u. And I want to replace the dx, I'm going to replace it with this 1/3 du. So in this case, like the last one, we said that the 2x's ended up canceling out when we substituted in. Well, there's nothing to cancel out with this 3 here. But what the nice thing about having kind of just like a constant is we can always pull those on the outside of the integral. So in this case, I'm going to take the constant out of the integral. So if there's nothing that ends up canceling and it's just a number, pull it out on the outside. So I'm going to write this as 1/3 times the integral of sine of u du. So that we're just left with on the inside of the integral something that's easy to take the antiderivative of. So at this point, I'm just going to take the antiderivative of sine of u. And once you take the antiderivative, you don't need the integral symbol anymore. But I am still going to pull down that 1/3 because that is still going to be part of our antiderivative. So if we think about the antiderivative of sine, that's going to give us a cosine. And again, I'm just keeping it in terms of u right now. And again, since this is an indefinite integral, I want to make sure that I'm putting plus c. I'm going to clean this up a little bit. So that's actually going to be negative 1/3 cosine of u plus c. But then my last step again is going to be to go back and substitute in what I know was u. So I'm going to go ahead and substitute back in that quantity of 3x plus 2. So my antiderivative of sine of 3x plus 2 dx is actually going to be negative 1/3 cosine of 3x plus 2 plus c. And if you did take the derivative of this, you should end up getting that sine of 3x plus 2. So you would have to use a chain rule here, but you should end up getting that. All right, so let's look at one more example. So now we're looking at x times the square root of x squared plus 1. So I'm going to, again, just kind of use my rule of thumb here, identify what's underneath my root, and that's what I'm going to call my u. So I'm going to call u x squared plus 1, take my derivative. So du is going to be 2x. Derivative of 1 would just be 0. So I'm going to do my times dx. And then I'm going to go ahead and solve for dx. So my dx is going to be equal to du over 2x. And again, depending on what we end up plugging back in or substituting back into this integral, you might want to write this as 1/2 times du over x. So just know that sometimes you might have to just kind of play around with that a little bit just to kind of get something that's going to work out nicely when you substitute back in. So let's do our substitution. So this is going to be the integral of x. Again, I didn't touch that outside x, so I don't want to do anything with that yet, but I'm going to go ahead and bring over the square root, substitute in my u for that x squared plus 1. And then I'm going to replace this dx, and I'm going to replace it with this version. So I'm going to replace it with the times 1/2 times du over x. And the reason that I'm doing that is because I'm noticing that over here, I only have an x to cancel out. And this 1/2 is going to be the constant that's going to get kind of pulled on the outside of my integral. So here my x's cancel out. I'm left with the integral of square root of u times 1/2 times du. But again, I'm going to go ahead and pull that 1/2 on the outside of my integral to kind of make something a little bit nicer to work with. So 1/2 of the integral of square root of u du. And this is something that we're going to be able to work with because we can, remember, write this square root of u as a fractional exponent. And just using the power rule, we're going to be able to take the antiderivative of u to the 1/2. So I'm going to go ahead and do that. So I'm going to pull down the 1/2, take the antiderivative of u to the 1/2. So that's going to be 1 over 1/2 plus 1 is 3/2, x to the 3/2, again, plus c. Oops, I'm changing my variable here. That should be a u. And I'm just going to clean this up a little bit. So it's going to be 2/3 u to the 3/2 plus c. And then I think that's just going to give us 1/3 u to the 3/2 plus c. And then at this point, now that I've got my kind of antiderivative cleaned up, then I'm going to go ahead and substitute u back in. So 1/3 times the quantity, I'm going to call this x squared plus 1. Since u was a binomial, I'm going to keep it in a set of parentheses, raised to the 3/2, and then plus c. And here is my indefinite integral of x times the square root of x squared plus 1 dx. Great. So I'm going to give you guys some practice to work on, and then we will kind of clean this up and go over some more examples together next week.